Okay, so hello everyone. My name is Andrea, and I'm a lecturer at the University of Bath. And together with David, who is a PhD student at the Alan Turing Institute, and Zach Conti, who is a postdoc at the Alan Turing Institute, but today he could not be with us because he has an academic commitment in the US. So altogether, we are the organizers of the Physics and Machine Learning meets Engineering seminar series. And the idea of this seminar series is to explore this new field of embedding physical knowledge within machine learning algorithm, but from the broader point of view of engineering applications. So today's speakers is Jiabu from the Virginia Tech. He is currently a PhD student. But before starting the seminar, I will ask David if he can introduce the speaker for us. Thank you.
Sure. Thanks, Andrea. So, yeah, it's a pleasure to introduce here today G, who is joining us from America. He's currently a PhD student in computer science at Virginia Tech with Dr. Anush Karpatni. I cannot so possibly pronounce this. Can you, Anush Karpat?
I think Karpatni. Yeah.
And his main focus is knowledge guided machine learning. Okay. Before his studies in the US, he earned a bachelor's degree in EE in China. He is interested in a variety of machine learning topics, including computer vision, graph representation, learning, etc. He has a few publications in the area of physics informed machine learning, with a more recent paper published in the Neural IPS 2021 on the topic of neural network planning. So we're hoping that you're gonna find his presentation interesting, and shall we hand over to you, G? And we're looking forward to see it, what you have to present for us today.
Yeah, sure. So shall I start now? Okay.
Go ahead. Yeah.
So today's topic, I want to talk about something, some challenges in physics-informed machine learning, which I encountered in the past works when I did some projects. So these materials are all based on the published ones, and also many of these slides and presentations are directly from my PhD preliminary exam. So just be free to use any of them, any materials I included in this presentation. Also, it's very welcome to cite any one of them. Okay, so as we see here that we have two major points that we want to cover. One is unique, one is challenges, right? So unique means it is only presented in the physics-informed machine learning, that it usually not is going to be a problem in conventional machine learning. So challenges means like currently we still cannot find a very good solution. Sometimes we can only find sort of like a trade-off, or we can try to compromise to find not the best solution for it. So we still have a lot of paths to go to solve it in the end. So the first part I want to talk about, I can give a brief recap or brief introduction about what is the physics-informed machine learning and why we need it in our case. So let's make a quick comparison with physics-informed and versus the conventional machine learning, which we can roughly categorize the machine learning domain into two categories. So the first one, conventional machine learning, is generally data-driven, like does not have too many prior knowledge get incorporated, like the computer vision and natural language processing. So when we talk about the prior knowledges, there's one form of prior knowledges is the physics knowledges we get from the scientific development. So we incorporate such a physics priors, for example, the equations. We know like there's some constraints equations or some observational bias, inductive bias, and learning bias. But these are these can come out of all sort of formulations or equations. So these can help us reduce the need for the data we want to use for training. So and improve generalization ability, performances, etc. So one of the good examples is the physics-informed neural networks. So for solving for the PDEs or incorporating the partial differential equation into the neural network training. So we will talk about that later. So here are some key factors influencing the generalization in machine learning. So which is one of the objectives in training the machine learning model. So we want the machine learning model to be generalizable. So there are two key factors. One is we wanted to have sufficiently representative training data. So the data has to be representative. Its quality has to be good. The amount of data for supervision has to be good, has to be sufficient. So once we have a good amount of data and the data quality is pretty good, and we can make sure we have enough model capacity to learn it, right? So we, of course, for example, like training a computer vision model, we cannot use a linear regression to do it. Right? The capacity is too low to solve the problem. It's too low to get a useful patterns from the data. So we need sufficient capacity. So it's it sort of comes to a case like it gives us a real world challenges. Like usually complex models wouldn't be an issue, right? So we can get very, very large models, and neural networks are proven to be very, very powerful. So right now, the biggest challenge right now is how to get enough data or how to get enough supervision to train such a big model. So as we see the model, when the model size grows larger and larger, so usually we need more and more data to support that capacity. But unfortunately, we're not able to get that amount of data, especially in, for example, scientific learning. We want to learn on scientific problems. We need to do simulations. We need to get the data. We need to do these, etc. But sometimes the simulation is really, really expensive. We cannot do that. So one solution is we're using the knowledges we have established in scientific developments. For example, we know the equations, right? So for example, we know how the heat is going to transfer. We know how the dynamics of some object is going to be, like for some sort of equation, some form of equations. And we put that as a constraint in training. So now the need for data can be reduced. So that's basically the physics informed machine learning and the advantage, like why we wanted to use it. So here is, I wanted to try to give another quick example, which is a simple one to show like how a PDE can be incorporated in training a very, very simple problem. So our objective is very simple. We want to just fit a target function. But the problem is we don't have enough points, and we don't have enough data to support that, right? So these red dots are the data we can observe. So the dashed lines are the ground truth, the target function, but we don't have enough data to support that high frequency information to learn it. So the model, when we train on it, so actually I trained a neural network to fit it. So this is the blue line is the result. The blue line is the neural network can only find out the low frequency hypothesis of its best, right? So if you do the regularization correctly, you will get something like this, a low frequency hypothesis. So, but the problem is it is far from the target function, how to do it. But we haven't, assuming we have some physical knowledges, right? So we know it's a sine wave, let's say, and we know its frequency is 6 by 2 pi hertz. And we know like we can normalize the amplitude, and this wave is normalized amplitude. But these information can be formulated into physical equations. Usually we already have the equation in many practical cases. So we say, okay, this is the equation we want to solve. Right? So this is governing equation. Now we put this into training as a loss function, loss term. Now we train the model to converge to a solution that satisfies both the data constraint, like from the data supervision. Also, it has to satisfy this equation. So now we get this the new blue line, which is a new model, which is physics-informed and neural networks results. See, right now, even with a little amount of data available and with additional knowledge getting to the trainings, we are able to get to the ground truth. So that's a toy example of showing how the physics prize can help us reduce the data need. So here we're going to discuss the problems after we already give a quick background of the physics informed machine learning, right? So the challenges is I want to discuss that into the next two parts. So the two parts, each part will cover one problem. So the part two, we're going to talk about like how the non-convex loss functions and competing objectives might hurt performance and might be a big problem in training a physics informed machine learning model. So the part three, we're going to talk about like do any like for example the experiences we learned from the conventional machine learning, are they generalizable? Are they transferable to the physics informed machine learning domain? So usually we rely on the experience we learn from the observations or the papers or the research from the general machine learning or conventional machine learning field, but sometimes it's not generalizable. I want to show like the model complexity trade-off can be different from the conventional machine learning to the physics informed machine learning. So in the end, it will have Q&A sessions. So let's come to the part two. The part two, we will talk about the non-convexity of the loss functions. As we know, like in the conventional machine learning, for example, computer vision and natural language processing, a lot of these fields, well-established fields. So the commonly used loss functions, for example, if for regression, we can normally use mean square error loss. For cross entropy loss, so this is commonly used for classification. So these loss terms are proven to be convex in training. So empirical evidences show that when training on the convex loss functions like this, so the neural network can actually converge quickly. So using these functions, we don't have a problem with these loss functions. But the problem is usually like in physics, like the physics formulations, that's the equation we want to use in the loss function. That equation sometimes not guaranteed to be convex. Some formulation can be non-convex. So here I'm going to use a simple example, like to show like the case to demonstrate like how the loss function can go wrong when the equation itself, the formulation itself is non-convex. So let's say we want a problem. So we want to identify the lowest eigenpairs of a symmetric matrix. So we can decompose such a symmetric real matrix into multiple eigenvalues, eigenpairs, but we're only interested in the lowest eigenvalue and the eigenvector that corresponds to the lowest eigenvalue, right? So there we have a lot of possible solutions can satisfy the eigen equation. There are n, like for example, by for decomposing the n by n matrix, then you got an n number of pairs that is valid, but only the lowest one we want trying to look at. So what is the physical meaning of this, right? So what is the practical problem, the real world problem behind it? So it is the time-independent Schrodinger equation in condensed matter theory. So let's say we have a time-independent Schrodinger equation that it can be rewritten as this. H is basically Hamiltonian of the system. So the psi is the wave function that describes the spin orientations. So the E is this system energy. So basically, we want to find out the lowest energy, which is the lowest eigenvalue. That is the most stable system. So we want to find out what is the most stable system in this Ising chain model. So this is basically an eigen decomposition problem, but only the lowest eigenvalue that is of our interest. So in here, usually people are going to use eigensolvers to do it. Like obviously, like eigensolver can do the job. But let's say we want to investigate, right? So if we have some problem that is similar to this, right? So then how the machine physics informed machine learning can it work, or can it have a problem when solving this problem? So a neural network tries to fit some data is generated by the solvers. So we use a hybrid approach. We will have some data generated out of the eigensolver, but a little amount of them. But for the majority of other points, we just generate the Hamiltonian matrix, but we don't generate the eigenvalue or eigenvectors of it. So we just use that as the input and try to minimize the error to the eigen equation, basically. So our input at this time is going to be H, which is Hamiltonian. We use the flattened version of Hamiltonian, the upper triangle with the symmetric upper triangle of Hamiltonian as input, flatten it out and put into the modulated perceptron, which is the feed-forward neural network, which is the most common, like most classic neural network. So our output will be a flattened vector of concatenation of the eigenvalues, also the eigenpairs. So it is all, for example, with a 16 for a 16 by 16 matrix. So our output dimension, the input dimension is going to be an upper triangle of that 16 by 16 matrix. So our output are going to be 1 by 16, which is the psi, the eigenvector, and one eigenvalue. So our output dimension is going to be 17 in this case, because we only want to predict one eigenpair. So in this particular example, that we might notice that why we want to do this, right? So because we want to say like, okay, this sort of a problem like eigen decomposition is not really interesting to us, right? We're never going to encounter such a problem. We never want to use a machine learning method to do it. So the advantage is not quite obvious, but it's actually there. So the advantage is it is actually very, very scalable and it's very easy to parallelize. So when I do small matrix decomposition, let's say 3 by 3 or 4 by 4, so if you just decompose one matrix, the neural network might be slower, like say 10 times slower to my experience, 10 times slower than a solver. But if I want to do 10 billion matrix decompositions, and I can do it in the batch way, I can feed a batch of 10 million matrices directly fit into neural networks, and it can solve it in 2 seconds. So it is almost 10 million times faster than the iterative solvers. And that is particularly interesting if you have many matrices to solve. So that is one of the reasons that we want to use it. For example, if we have optical systems, we have some system needs a lot of matrices to be decomposed, and you can use a neural network to approximate it. Like if we don't require very high accuracy in the decomposition, we just want a rough decomposition. So that's where we can use it. So here we come to the training neural network, right? So in the classical way of training neural network, it is when it's unconstrained, it just train it on the data that just get MSE that is using gradient descent methods. Basically using backpropagation, we can update the parameter of the network and find out its approximation of the real functional mapping. So, but in here, we don't use MSE as we speak about before. We don't use MSE, we don't use cross entropy, those convex functions, but we rather use the residual of the Schrodinger equation. So we have a constraint optimization problem over here. So, but we added the constraint into the loss function to train it. So let's say we want the left side equal to the right side. So of course we can take the subtraction of it and take the norm value of it. So these basically is the residual. So to avoid the trivial solution become 0, to avoid the eigenvector to become 0, we need to normalize it. Otherwise the model will quickly predict all 0 solutions. So when we normalize it, this becomes our S loss, which is we say the Schrodinger loss, right? So we wanted to satisfy the Schrodinger equation to satisfy the constraint. So we have another loss function, let's say. It's the simplest formulation to try to reduce the energy, which is basically the eigenvalue predictions. Just add a penalty term to the predicted eigenvalue. So now we try to minimize the eigenvalue in the same time. So we have an E loss term. So in total, in this physics-informed loss function formulations, now we have 2 loss terms. One is we try to satisfy Schrodinger equation. One, we try to minimize the eigenvalue. Basically, the eigenvalue of the Hamiltonian. So if we just plus them, do a summation of the together, like that's the most simplest way to do it, right? So that's also the most common way of doing this. But does it work? So we might be like overconfident in some of the formulations when the equation is really complicated. We cannot really see the convexity of it, right? Is it really a convex function? Is it really not unconvex, non-convex function? We cannot see it, but here we are pretty much very sure it is a non-convex function. Why is that? Because when we have things like, so this is the data-driven label, so which is MSE. When we train the S-loss, so S-loss is just trying to satisfy the Schrodinger equation. So we know like every eigenpair can have exactly zero values for the S-loss. So there are all minima of S-loss. So of course we are training something that the loss function is non-convex. And we have an additional term, the penalty for the energy. So which is monotonic, we can think, monotonic with respect to the eigenvalue of the Hamiltonian. So only problem comes from the S-loss. S-loss itself is non-convex. So when we plug in this loss function, this entire training from the loss function for training becomes non-convex. So would it have a problem? So intuitively, it definitely would have a problem. Like so the model can just fall into one of the minima, can predict any eigenpairs in the reality. It's probably not going to find out the lowest eigenvalue in the prediction. So actually, that is what I observed. If you just directly train the model using physics-informed laws and with some help from data-driven points, because if you don't have these points and the model just quickly converges to any eigenvalues, any eigenpairs. So if we add some little bit amount of data, that model training is stabilized, but it's still not able to find out the lowest eigenvalues like every time. So we needed some ways to solve that problem. So we try to formulate this problem, like we try to discuss the competing physics objectives, because we believe that non-convex optimization, when it's actually in which form it hurt our training. So in the non-convex optimization, it is actually we're going to have the loss term at some particular stage of training. The gradient from different loss terms might be opposite. They might just conflict with each other. So the model is going nowhere, just stuck at one of the minima. So that's pretty obvious. Like for example, in here, so the gradient direction is being pointed out by the arrows, right? So by doing a gradient descent, these are the direction that the model will go, the S loss. For example, by doing one gradient update, so the S loss value is going to decrease like this. So the green arrows, let's say, the model in parameter space, let's say we use one dimension to visualize it. So the left side, so at this area, so the parameter, on this dimension, the parameter has to go left to minimize S loss. But at this particular area, so the parameter has to go right, which is increase the parameter to reduce S loss. But there's a problem. For example, the MSE plus E loss, which is the energy loss, penalty term for the eigenvalue, it might have a different direction. See, in order to reduce the MSE plus E loss, so at this particular area, so the parameter has to go left. Okay? So we now have a problem. Like the model, the parameter has to go right to minimize S loss. The parameter has to go left to minimize E loss. So they have conflicting gradient terms with each other. So the gradient angles are going to be different. So model, when it reaches the balance, like the model just stuck at the one local minima, cannot get out. So this is the overall loss. Like I just try to give try to show like what is going to be like. It's not very strict. So it is like, for example, here we have one local minima, the other local minima, another local minima, and this global minima we want to reach. But there's many local minimas in between. So this is the true solution, which is the global minima of the overall loss. So now we introduce one concept that is, we know like every non-convex function will have some region that's locally convex, right? But let's define the local convex region, locally convex region that happen to have one minima, which is a global minima, and that region we define it as the safe zone, meaning that if our model is somewhat like some way like we can reach this, the model can reach this particular region, the locally convex safe zone, then the model can definitely converge to the global minima using gradient descent. So the only problem is how to get to this safe zone, right? So we can get, so now I will give a background of the continuation method for non-convex optimization. So this is first introduced in 1987 by A. Blake, so for Dr. Blake too, in the visual reconstruction book. So it is try to, so they try to use this method. So this to solve the non-convex optimization problem. Basically, so when we have the ground truth, let's say like this, so the real loss function look like this is really non-convex. The surface is pretty rough. It's not really easy to optimize. So we can sort of smoothen out the entire loss function, get a smoother version of it. And we can try to get to roughly like, we can get to a minimum, which is in the spatial proximity. It is very close to the true global minimum. So we use this approximation of the ground truth, which is low frequency approximation of the real target loss function we want to minimize. So we just do this and adding more and more high frequency details and eventually we can get to the global minima, or at least a good minimum. So in 2009, so Joshua Bengio actually introduced that to try to discuss a problem in non-convex optimization in neural network. So here we have the curriculum weighting that we try to use the continuation method to solve our problems right now, because we have competing loss terms and we have a non-convex loss term, which is the S loss. So how can we use the continuation method? So we name it as curriculum weighting. So S loss, when we actually add a lambda before it, so this term is a constant, is a scalar value, basically the weight or coefficient of the last loss. When we just reduce it, and we were able to get a smoother, less. And so we reduce the magnitude of S loss, so the loss surface can be smoother. So this is the adaptive tuning strategy that we are getting. So the S loss initial epochs, we're going to make it very small. The lambda S is going to be very small, that we just make it the magnitude to be reduced. And the E loss initial epochs, we make it large. So we have a superposition of the both of the S loss and E loss. So the entire domain will be dominated. The entire loss function, the geometry, the landscape is going to be dominated by the E loss, which is a nice surface because it's monotonic with respect to the E, the energy eigenvalue. So after training to some epochs, when the model parameters reaches some the left side, let's say left side, when it reaches a set of parameters can predict low eigenvalues, then we gradually increase the weights of the S loss, and the loss surface gets more and more rough, as we show in the continuation method. So the E loss will get reduced because E loss, as we use the exponential formulation, so it will always be positive. So we want it to be minimized. We don't want E loss anymore in the later stages. We want to only try to fine tune on the S loss, which is the eigen equation. So now we have the curriculum weighting. So we have the formulation using exponential weightings, basically the sigmoid. So sigmoid can prevent a nice and smooth transition. Basically, the increasing the lambda S and reduce the lambda E. We use both sigmoid functions to do the job. So the training of the coffee pigeon, and we named our model as coffee pigeon, basically for competing physics objectives. So physics guided neural networks. So when we train the network, we will have labeling, a labeled training. So labeled training data is coming out of eigensolvers. We just solve a little bit amount of data out. So use a little bit amount of high Hamiltonian matrices and solve them and get the ground truth labels and to stabilize the training, just for the sake of training stability. So now we have the unlabeled training sets. So these are the vast majority of the Hamiltonians, which we don't have the solutions. We don't have the eigenvalues, eigenvectors, the lowest eigenpaths available in training. Well, we use these generated Hamiltonian matrices in training as well. We try to minimize the E loss and S loss over it. So this is our training strategy. So it's some sort of a hybrid training, both data-driven and physics-informed. So here are the results. So try to give some insight over here is like the black box and then only trains using a lot of data. It does not have any physics-informed. Does not have any physics-informed loss functions. So we see that the cosine similarity basically measures how similar the eigenvectors is to the ground truth, because the magnitude doesn't make sense now. We only want to know the cosine overlap, cosine similarity to the eigenvector. So cosine similarity shows the black box and then do a fairly good job, but it's not going to be, we are not going to be satisfied with that because we want to be pretty accurate. At least we wanted to get 99% of cosine similarity. So all other baselines, either we remove an S loss, either we remove an E loss, either we don't use that data. So this is, we don't use data point. Labeling means we don't use any data generated by the eigensolvers. We just train directly on the physics-informed loss, and the model performance is pretty unstable. So if we add a little bit of data and we use our tuning strategy to avoid the local minimas, then we are actually able to get 99.5% of cosine similarities. So that is pretty, I would say, pretty impressive in terms of the cosine similarities. We are able to get the eigenvalue, and the speed is super fast. As I said, 10 million times faster if you have many matrices to solve. So this is runtime scalability, as we say, that the throughput, we can get to a whopping throughput of 3 million inputs, 3 million matrices per second for 16 by 16 matrices. We can process using our own one GPU, which is not a high-end GPU, can process 300 million matrices per second. So I don't think any solver right now can do that job, like using one GPU. So now we have finished the discussion on the potential problem we might face from the non-convex optimization non-convex loss function formulation from the equations we might get from the physics. But that's not usually common in the conventional machine learning. So right now we want to talk about another topic, basically. It is the model complexity trade-offs, which is a long discussion that has still been discussing to nowadays, like in the conventional machine learning, in the entire machine learning community. We want to specifically focus on the physics-informed machine learning. So what's the difference there? So let's talk about the model complexity trade-offs in the conventional machine learning. So we have bias and the variance trade-off. So basically, when the model gets too complicated, the model just fits the training data very well. And then you have a large variance when you're predicting something that is not presented in the training data. That is a common phenomenon called overfitting, which is the biggest issue, one of the biggest problems in machine learning. So models right now in the conventional machine learning, which is data-driven, are specifically designed to avoid overfitting. For example, we usually pair with regularizations when we train the model. We try to have dropouts. For example, many vision models, many like the natural language processing model, like transformers, those will have a lot of dropout layers. We will have pooling layers. So those layers will have regularization effects. Also, even the normalization layer can have regularization effect. But those are usually presented in the conventional machine learning or deep learning models. So the question is, can we use directly off-shelf conventional machine learning or deep learning models to do the physics-informed machine learning? Or are there any better way to do that? Right, so does this model complexity trade-off still holds in the physics-informed scenarios? So one thing to notice that is, as we speak about before, right? So large models need more data or more supervision to support that capacity. So luckily, like in physics informed, we have an equation. One equation is worth, that one equation worth this infinite number of data points, right? Because it is a continuous representation and it represents infinite number of data. So we don't quite concerned about the amount of data or supervision that is available to train the model. So the model can train to a very, very rich amount of supervision coming from the physics like constraints. That is a usual case. So that brought up to a question. So if we have enough supervision, what if the physics formulation behind it is really complicated? What if the Grunschutz function the model tries to fit is really, really, really complicated? Let's say if it is really, really high frequency, right? So because we only care about right now the model the capacity. Remember in the beginning, I talked about like the two aspects that affects the generalization. One is the number of data with supervision affects the training. The second is how the model capacity, like you can learn the data or the supervisions. So since we don't concern about the first point, the number of supervisions, now we need to concern about the second point, the model capacity. So I'm showing the composition of the sign functions together. They are pretty much very high frequencies. So I'm training a neural network just to fit using mean square error loss. Try just to fit that function. Try to investigate whether our neural network is good enough right now to fit complicated functions. The problem is it is not that good. So this model is already big. And when we trained it to fit the high frequency values, it is able to fit it eventually, but you probably need millions epochs to fit it. It's very, very, very slow to fit high frequency values. So also it requires a big model to do so. So it is not very parameter efficient. It is very slow. The convergence is very slow in training. So we need a long time to train, which is not a pretty good option currently using our current deep learning neural network setups. So by the way, I'm using 10H activation function, which is a pretty common activation function in the physics informed machine learning communities. So our question becomes, oh, we have observed like deep neural networks, the conventional formulations is not that good. So can we have a better formulation? Can we have a better version of it? Right, so now we try to propose another formulation of the neural network to replace the conventional formulation of the neural network. That we add some additional nonlinearity to every layer, every neuron to make them more nonlinear than before. And also we want them to be efficient. We cannot add too many computational costs. So we added quadratic functions to it. So basically in the conventional deep neural network feed-forward modulated perceptrons, so the network is a weighted sum, and then after it is the nonlinear activation function. So inside it's still linear, right? So we relies on the nonlinear activation to give us the nonlinearity. Like that's the only where we get nonlinearity. By stacking more layers and the model goes deep, and we are more efficient. You can more efficiently get to higher nonlinearity. It can obtain the capacity to learn highly nonlinear functions. But we have shown that it's not probably not enough. So now we change the formulation that before activation to raise the power, the order to 2, like raise the power to 2. Now we have a quadratic formulation. Basically, we have 2 weight matrices, and we have additional quadratic term. So what is called residual, because we're learning the residual, quadratic residual. So this is the only modification to the network. So the question is how good it is, right? So can we expect any magic coming out of this quadratic term? So we try to fit, again, the same function. You see, in 20,000 epochs, it fits perfectly to the Grunschutz function. The fit is quite fast on the high frequency information, but it does not overfit to it. It fits quite well and fits not exceed that limit. It does not overfit. So the model significantly improves the training convergence speed, as well as it is able to reduce the amount of parameters we need to train for it. I will show it later in the later examples. So this is briefly brief framework of the physics-informed neural networks. Basically, it's try to fit the PDE residuals and we have a set of 4 PDE formulations, and we'll try to add that into the loss function, and we'll try to train on it. So for these materials, so yeah, it might take a long time to cover the background for physics-informed neural networks. So I would recommend to read the materials, the original PIM paper, if you are really interested in that. So I'm basically using this PIM structure, nothing different. Only difference is sorry. The only difference is network architecture. I just replaced the network. That's all all the modifications I did. So by replacing the model we are using to train to learn the PDEs, we can see what's the difference between different models. But these are the set of equations I tested out, tested model performances. So these are coming out of the original PIM paper. So when we try to compare with the forward problems, the forward problems is given initial and boundary conditions. We'll try to find out what is the solution of that PDE. So you see, we have an original PIM basically using the deep neural networks, and we have QRES, which is a new architecture. You see, with half of the number of the parameters, the same training epochs, we're able to get better results, the better accuracies. For both the Schrödinger and Alencon equation. So for the Alencon is even more significant. We have less than 1/4 of the number of parameters, and then we are still able to get higher accuracy. So meaning this is actually the bottleneck of the model capacity is actually the bottleneck for training physics-informed neural networks. So for another forward problem, which is another set of forward problem, which is the Navier-Stokes equation, Burgers equation, and the KTV equation. So we have these equations. The trend is still consistent. Right now, we are interested in, for example, when we have the same number of parameters, can we do better? The accuracy is better. So if we have a less number of parameters, we are still able to do better. If we are going to have a less number of training epochs, we are still able to do better. So that means the QRS networks is truly improved the convergence speed, as well as it requires less number of parameters to get a better performances in training the PIM. So we have plotted out the loss curve. So see the convergence of QRS is approximately 4 times faster than the original deep neural network formulations. That is consistent to all the experiments. So this is the final analysis that I did is trying to visualize the error map in the predictions. Try to actually to see where the error occurs in the original PIM and why the QRS did better. So this is the formulation that we have the error like a map after training 50,000 epochs. You see there is a high error region to where it has the high frequency patterns. So here we see it has left side, we have the high frequency patterns. A lot of error occurs over this particular region. If we use the quadratic neurons, right now you see the high error regions got this resolved, even though for the overall mean square error is going to be a little slightly different, but this area of interest is very, very different. So because the errors got meaned out, like it got averaged out if we just took the mean value of the entire field, which we have many fields, which is very easy to learn. So that means quadratic neurons actually indeed helps. Yeah, so here we come to the final concluding remarks and takeaway messages. So we have covered the 2 problems, like the 2 example problems and demonstrate the 2 challenges I encountered in the past when I do the physics-informed machine learning projects. So in the study, we have shown that the non-convex formulations can be a problem. Like sometimes we will have the equations. It can be differential equations, or it can be like normal ordinary equations. But those equations sometimes we're not very sure, like whether it were introduce non-convexity, or it's not so obvious sometimes, or sometimes it is obvious. So whenever it has non-convexity, we should be extra careful, like what are the loss function terms are introduced into the loss function. Sometimes I see people probably don't quite pay a lot of attention when they just concatenate a lot of like loss terms in them to their training objective. So that's probably very dangerous, I think. We should understand each loss terms, whether they introduce non-convexity into the loss function or otherwise might have a problem. So that's what I show. So, but that's actually brings up another topic. Like maybe we should rethink the rules that we learn from the experiences of dealing with conventional machine learning. There are a bunch of papers, a lot of papers in conventional machine learning. Everyone talks about it, like everyone gives an insights, but how many insights can actually apply to physics-informed machine learning? How many differences we should expect when we try to transfer the knowledge from conventional machine learning to physics-informed machine learning? How many unique aspects we expect for the physics-informed machine learning? For example, like directly using the off-the-shelf deep learning models. For example, when we want to do turbulence flow predictions, many people use CNN, convolution networks. Many people use GANs, for example, and they just took some state-of-the-art vision models, like computer vision models. They just look at the leaderboard, which is the best vision model, and now they just try to use that model to predict our flow field. But it might be the best case. It might be over smooth. It might be maybe over regularized. It might not have enough capacity. Might be the architecture doesn't make sense, right? So we just use it. So that probably not going to be the optimal case. So we should rethink what is the optimal architecture we want to use, and what is the optimal rules? What are the rules we're trying to expect that we're trying to transfer the knowledges from conventional machine and physics-informed machine learning. So I think that's all the takeaway messages of this talk. Yeah. Thank you very much for listening. So. Yeah.
Oh, thank you, Jeff, for the interesting talk. So, is there any question from the audience? So maybe I can break the ice, and could you please go back to slide 43?
Sure.
Oh, okay. Yeah, I can see that. Okay, so I was wondering, yeah. So in general, for instance, in the case of the Allen-Kahn equation, like there are also ways of solving it numerically, for instance, using the Merriman, the MBO scheme, so which is the mean curvature flow. So I mean, I was wondering, like, with respect to these more traditional methods to solve certain type of equations, how does your approach compare with?
So just trying to see whether I understand correctly, like comparing with the traditional solving scheme, numerical scheme, right? So yeah. How does the physics-informed neural networks compare to those methods? Yeah, this is actually quite good, right? Quite a good point, because this is actually a point that's been like heavily discussed, like it's been discussed everywhere. Like, what is the practical use of the physics-informed neural networks? If people say like, I have these equations, but I have those well-developed schemes, like numerical schemes to solve them, right? So then how does your like physics-informed neural network compare with them? So this is actually physics-informed neural network is actually not a very new one. So it's actually being proposed by Dr. Mazia Razi in 2017. I used exactly their code. I even used their code so to change the network. So the problem is the physics-informed neural network for forward problems. For example, solving Allen-Kahn, you have boundary conditions, you have initial conditions. And the solving does not have any practical values for current stages because it's pretty slow. You need to train it. But for the solver, just solving it. For example, solve a linear system or iterative solving. And it might take, like say, for a simple case, it might take seconds or take minutes. Like the most complicated one, like large scale, it might take hours, but that's most unlikely. But for neural networks to train on that, it might take an hours to train for a simple one. So the forward problems right now just show that neural network is able to do it then. So one difference is like the numerical methods, whatever the method is, we need some sort of approximation for the derivatives or gradients. Let's say the derivatives need to be approximated, like a finite element, finite differences. But in neural network approaches, those are actual analytical gradings. So we are actually using analytical methods to solve the equations. So that might be a case like when we have a very, very complicated equation, for example, some certain variation of a Navier-Stokes is really, really difficult to solve, that you need fine-tune the grid very, very well to solve it. Otherwise, you either have a high error, you either have an instability in solving in the skins, and the tuning is really a pain. So if you just apply an analytical version of the solver, basically the neural network, you don't need to tune them, just apply a grid or apply some random samples of points and train it. Though it's going to be slower, but it works, right? So for example, like we don't need to tune the grids for like months sometimes and just apply the network and it will solve. So that's the advantage comparing to numerical scheme. Yeah.
So is a question from the audience, Subhash.
Yeah, hi. Thanks for the nice talk. So I have a question. How generalizable is your method, or should we look at individual problems and figure out these scalings, how to tune the scalings? Because I think your approach was for a specific problem, right? So can this be generalized to different loss functions?
Oh, so I reckon you talk about this approach, right? So the first example. Yeah, so that is actually, I would probably even call it a heuristics because it's not really a generalizable method itself. So the major objective is just trying to show like when we get these objectives, it's not really an easy problem to solve it, right? So a continuation method, like this can't be a generalizable method. So probably you can develop another method, another scheme, do similar tuning strategy. For example, if you know which term actually introduces non-convexity, then you can just reduce it and train on other loss terms initially and have a small other and gradually introduce that loss term which has a problem. So I think I suppose like I think this method alone and my approach is not generalizable, but I think the idea behind this might be generalizable.
Yeah. I like the intuition though. Thanks.
Yeah, thank you.
So we have another question, Aditya.
And thank you so much, Sanjay. And thank you, G, for this wonderful talk. I had a question on your introductory slide of the QRES architecture. Could you go to that slide, please?
Oh, sorry. So which slide again?
The QRES, the slide when you introduced introducing the quadratic terms, and I think it's this one. Yeah. So here, so we see that the classic feed-forward network only has a W, like weighting, a set of weights. So here in your case, you have a W1 and a W2. So what exactly are two W1 and W2 represent here? And forgive me if this is silly, I don't have much experience myself.
Oh, no problem. This is a good question. So here, as we see, I have two weight matrices to learn these quadratic formulations, right? So W1, W2 are two matrices of the same shape. So when you look at it, the normal neural network, you have Wx plus V, right? So I just duplicate this matrix. Let's say I duplicate to get another matrix, which is the same shape to this formulation. You can think about like you have two matrices of the same shape. So now when you W1x, just map the x input to the another dimension, like the hidden dimension H, and you have another matrix, which is also learnable. And so you map it to another H2. So you will have a hidden dimension H, for example, H1 times H2 plus H1 plus V. So that is actually going to cover the entire quadratic functional space.
Okay, I think I got it. Yeah, thank you so much.
Yeah, thank you.
Okay, so I mean, we are just past 2 p.m. here in the UK. So I'd like to thank our speaker again. So thank you, Jibu, for joining us. And well, in case, of course, like other members of the audience have another speaker to suggest or would like to contact G, please let us know. And of course, we can put you in contact or try to contact another potential speaker. Okay, so I wish you a great afternoon, and I'll see you in 2 weeks' time.
Yes, thank you all. Have a great afternoon.
Thanks again, Jim.
Thank you.